Let's take a look at a couple of other operations. We said that one of the main reasons we use the tree is that it allows us to find information in a quicker fashion. So let's see how we search a binary search tree for a particular value. So for instance, if we're looking for the value 43, we begin at the root and we ask ourselves, is the value at the root, i.e. 31, is it equal to 43? So at each point, we're going to ask, is it equal to? And if the answer to that is yes, then we will immediately return true. If the answer to that is no, then we will ask if the value we're looking for is less than the value at the node. And if that is not the case, we will then ask if that value is greater than the value at the node. Okay? And so we get the 43 and we ask, is 31 equal to 43? It is not. So we ask, is 43 less than the 31 that's here? It is not. Is 43 greater than 31? It is. So we traverse to the 59 and then we begin the whole process again. We ask whether 59 is the value, whether 43 is the value at the node, and it is not. So then we ask, is 43 less than the value at the node? It is. So we travel to this particular node and we ask, is this 43 the value that I'm looking for? And it is. So in this case, we will return true. Okay. Now let's say that we're going to look for the value 17. We begin at the root again, and we say, is 17 equal to the value at the root, which is 31? No, it is not. Is 17 less than the value at the root? Yes, it is. So we travel down here to the 19. And we ask, is 17 the value at this particular location? No, it is not. It's 19. Is 17 less than the value at this location? Yes, this value is 19, so 17 is less than 19. So I travel down to the left subtree. And then I ask myself, is 17 equal to the value that's at this particular node? It is not. So then I ask, is the 17 I'm looking for, is it less than this value? It is not less than 7. So then I ask, is the 17 I'm looking for, is it greater than this value? It is. And so I traverse down this particular pointer, and then I notice that it's a null pointer. I haven't found it. Therefore, I will return false in that particular case. Okay. So now we've seen how we insert information into a tree, a binary search tree. We've seen how we retrieve information from a binary search tree. Let's take a look at how we delete information from the binary search tree. It turns out that this is not as straightforward. There are 3 individual cases we must deal with when we decide to delete a node from a binary search tree. Okay, so the first case is the simplest case. If the node to be deleted is a leaf node, then we just simply replace the parent node's pointer with the null pointer. So in other words, if I'm deleting from this particular tree, if I'm deleting the value 7, and I travel down here and I realize that 7 is in fact a leaf node, all I must do is replace this node, this link that was previously pointing to 7, make it point to null. And so it's going to look like this. And I'm going to release, I'm going to do a delete, right? Delete meaning the opposite of new. I'm going to delete the node and give that memory back to the system, okay? So if I'm deleting a leaf node from a binary search tree, it's really straightforward. Just take its parent node and make it null because it has no additional children. Let's take a look at the other case, which is I'm deleting a node that has at least one child from the binary search tree, okay? So the behavior here then is that I must make that parent pointer, the parent of the node that's being deleted becomes the parent of the node's child, right? So let's look at this. If I'm deleting from this particular one, if I'm deleting node number 9, this value, you notice that it has a single child, right? So this is not like the previous case where it was a leaf node. This is not a leaf node. It has a child. But it's fairly straightforward because all I must do is take this link that was previously pointing to the 19 and make it point down to the 7, and then I can just scratch this node, i.e. delete it, give it back to the memory manager, right? And that gives us this tree where 31 is still parent of 59 and 59 is still parent of 43, just like on this side. But 31 is now the parent of 7 because 19 has been deleted. And we preserve the binary search tree property in the sense that every node that has a value less than a particular node shows up in its left subtree, and every node that has a value greater than the particular node, 31 in this case, shows up in the right subtree. 43 and 59 are both greater than 31. Okay, the final case is a little bit more involved, and it is how we delete a node that has 2 children from a binary search tree. Okay, so we've looked at deleting a node that is a leaf node, i.e. it has no children. We've looked at deleting a node that has a single child. Okay, and so we will now take a look at how to delete a node that has 2 children. Okay, and the approach here is to take a look at either the leftmost node of the right subtree or the rightmost node of the left subtree. We're going to take that value and we're going to copy it to the node that's being deleted. And hopefully you can think of why that's the case. In essence, those 2 candidate nodes, we're only going to operate on one of those. We're going to pick one of those 2. But those 2 candidate nodes have the closest value to the node that's being deleted. And I'll give you a graphic here in a second that will show you that. So let's say that we chose the leftmost node of the right subtree. We're going to take the value at that particular node and we're going to copy it to the node that is being deleted. Okay, and then we're going to actually delete that leftmost node of the right subtree or rightmost node of the left subtree. Okay, so here's some notes that are worth mentioning. The leftmost node of the right subtree or the rightmost node of the left subtree, in both of these cases, these nodes have at most one child, okay? And hopefully you can see that, because if I could travel further left, then that means that I'm not at the leftmost node of the right subtree, right? So at most, these will have a single child, okay? And there's a symmetric case depending on which one of these we pick. And this approach can be inefficient, but it is flexible, which is why we use it. So let's take a look at a graphic that will hopefully help you understand this a little better. Okay, so this method is called delete by copying. And again, we're trying to pluck out a node that has two children out of this binary search tree. So here's a binary search tree, and we decide we're going to delete node 2. If you notice, node 2 has two children. It has 1 as its left child, and it has 5 as its right child. And so we're going to pick, so let's take a look at the right subtree, okay? And let's pick the leftmost node of the right subtree. Which one is that? That's going to be the 3, right? So I'm going to look at the right subtree from the perspective of the 2 that I'm trying to remove from this tree. And I'm going to look at the right subtree, and I'm going to pick the leftmost node in the right subtree. And hopefully you can see that that's in fact the 3. And so I'm going to take that value, that 3, and I'm going to copy it where that 2 is, and that'll look like this, okay? So I've copied the 3 up because, again, we're getting rid of this guy, right? We're trying to get rid of this guy. Right? We're trying to have this node removed. And so the node is physically still there. So I copy the value of the leftmost of the right subtree. I copy that value into the node. And then I must delete that particular node. Well, in removing this 3, this will either be a childless node, or it will have only a single child, okay? And as you see, the 3 has a single right child, which is 4, okay? And so we will apply the previous method we talked about, which is to delete this 3, I simply connect the 5 to the 4, giving me this particular tree. And as you notice, we will actually delete the node, the node 3 from the tree. We will release that back to the memory manager so that it can be applied for later uses, okay? And so we're left with the resulting subtree that is shown on the right.